dark matters. So there is a dark side to the universe. I'll be telling you a little bit about that. But it's sort of interesting that the dark stuff in general is of great appeal in many areas. So here's a series of paintings by the US artist Alan McCollum, which are entirely black. But you see, what does vary is the frame and the shape. so you know, in a sense, what I'm going to tell you is a scientific analog of this. The dark stuff of the universe comes in different forms, different varieties, but it's inevitably dark and essentially invisible, and we have to try very hard to think of clever ways to detect it, to convince ourselves that indeed it really exists. So here in a nutshell is what we see in the expanding universe. So this is the entire history of the universe, actually, from the very mysterious beginning that we don't see but we infer. But when we peer through telescopes, we do see this faint glow from the beginning, which was a few 100,000 years after the Big Bang, actually. But after that, there was a phase when there was nothing visible so far. We call that the Dark Ages. And then, as time goes on, stars form. And this is what we're beginning to map out with our telescopes. Certainly the nearer part to us. We're over here, basically, looking back in time. And the universe is full of galaxies, and it's all taken some nearly 14 billion years since the Big Bang. That's our current view. And right at the very end, the expansion is beginning to speed up a little bit, to accelerate. And I'll come to that in a minute. That's another form of dark stuff, so that we are worrying a lot about in cosmology. So this is what we don't see. So we see the atoms, we're made of atoms, but there's all this stuff which we call dark matter. It's thought to be cold dark. I'll explain that in a moment too. But there's even more dark stuff in the form of dark energy, which fills the universe and is causing that recent acceleration that you noticed in that last glimpse, that last timeline of the universe. We believe it's responsible. So, 96% of the universe is dark. That's a lot. And, clearly, unless we can get to grips with this and have a better understanding of what it is, we're not getting very far in our comprehension of the universe and, indeed where we came from, which is our ultimate goal here, to try to figure that out. So let me begin with the dominant component, which we call dark energy. And this is responsible for this recent sudden pickup in speed of the expansion, this acceleration of the universe. We all know it's the expanding universe, but why is it's expanding faster and faster as in the recent past, as we determine by looking at distant galaxies? So the story goes back to Georges Lemaître, who was an ordained priest, but around the time he first did his PhD, just before when he was about becoming ordained, he was a cosmologist, and he was very interested in Einstein's theory of general relativity, which had really just been around for a few years, and he was interested in the universe. And he understood something that Einstein did not understand, namely that the universe could quite plausibly be expanding. And so in his sketchbook in 1927, where he, like many good scientists, he wrote down all his ideas. He sketched out his ideas for the solutions of Einstein's equations for the expanding universe. And so these are different theories, different models of the expanding universe, some of which get larger and larger, then come back, and there's a big crunch. Okay, that was one option. Another option was just expanding forever and ever and ever, of just gradually slowing down, but never really stopping. And a final one, a third class, was a universe which suddenly begins accelerating towards the very end. And so Lemaître had these ideas, and what was also quite remarkable was he went to talk to the astronomers in California, Pasadena, and he got hold of the data, which was known at that time to a number of them on the galaxies and their galaxy motions, essentially from the Doppler shift of light. And so he looked at the comparison. Of course, the data was very, very sparse in those days. Could he actually see the acceleration? The answer was no, he couldn't. But before I show you what Lemaître found, let's just go back to where all this came from, which was Einstein's new theory of gravity. And so Einstein had the brilliant idea that one can understand gravity much better as being due to space not being Euclidean, as we're, three angles of a triangle up to 180 degrees, we're taught in school, but in fact, because of the presence of gravity, is slightly curved. And so the three angles would add up to a bit less because space is being curved, and that's the equivalent of having mass. And so here is sort of a cartoon of what would happen around an object, a compact object. Could be a black hole, it could be a star even, it's a small effect for a star. So space is somehow, and by measuring this property of space, you can basically determine the properties of matter that you can't see. I mean, some matter you can see as stars, but if there was dark matter, this is brilliant because it would affect space, and you can measure by studying light rays that go through space. They don't go quite in straight lines. You can infer stuff about dark matter. So that was the idea, and so Einstein then had this idea that the curvature of space was basically sourced by mass. Mass and energy are similar, and also momentum. And he wrote all this down in an equation. Now, I'm not going to, I just want to show you this schematically because the idea behind this is very simple, actually. So, complicated algebra, in fact, this was introducing the tensor calculus, it is said, is what was the point in cosmology which the theologians mostly left the field and the scientists came in, in the 1920s. But so you have, the curvature, and you have all this stuff which is the matter. And Einstein was very worried because he realized because of gravity the universe would collapse, and that would be a nasty thing. So he introduced a new form of repulsion, of anti-gravity, in this thing with a Greek letter lambda in front. And we call that the cosmic constant. So it was unpleasant, it was artificial. He did not know about the expanding universe. And if he had known about that, he would not have needed to have done this. So Lemaître came along and he said, well, we can, this was what Einstein wanted. He wanted basically gravity and something to counter gravity. But if the universe, as in the data that Lemaître was able to get his hands on, that Einstein was unaware of at the time, this would give you something new. And so, and Lemaître realized also that this anti-gravity, this lambda thing that Einstein had invented, he was the first person to give a physical interpretation to it. It was a form of energy, but because it's a form of energy with a minus sign in front, it acts like anti-gravity. It can accelerate the universe. And so in this classic paper in 1933, Lemaître talked about the energy of nothing, basically the vacuum, which we have a modern understanding in terms of quantum theory now, a little better. And this acts like the opposite of gravity. It can push things apart. So that was Lemaître's idea. And of course, here was his first attempt, the first attempt, to look at the data. So at that time, they just measured, each point is the redshift of a galaxy, the velocity of a galaxy. And Lemaître's idea was that the further away the galaxy in his models, the further they should be speeding up. And if he was right about acceleration, they should be speeding up even more the further you went. They should not be a straight line, but the line should curve upwards eventually. Now, you couldn't see that. The data was ridiculously noisy. But nevertheless, it did support the idea of the expanding universe. The further away, the faster things were moving, which would mean that you did not need necessarily to have this weird force which gave you acceleration, this lambda thing that Einstein had conjectured. There was no need for it anymore. Okay, so this was in 1927. So Lemaître was a very modest person, and he actually published his results in French in an obscure journal in Belgium, and it was not widely known. And so 2 years later, Edwin Hubble, American astronomer, also rediscovered, unaware of Lemaître's work completely, that there was indeed a relation between the speed of a galaxy and its distance from us, and this was the origin of the modern theory of the expanding universe, and this is called Hubble's law, not Lemaître's law, but for reasons that are quite common in physics, actually. The original discoverer sometimes does get forgotten. But it was a year or two later when Lemaître's ideas were recognized, translated into English, etc., that it's become known, much more widely known about Lemaître's contribution. So here's the modern data, just to show you. We flash forward now to basically 70 years forward in time, 60, 70 years forward in time. And you can see that if I go to this straight line would be the expanding universe with no acceleration, and all the data far away, when the universe is half its present age, is going a little bit too fast, which means that there's acceleration. And so, indeed, Lemaître could not detect this acceleration. He hypothesized about it, but it really seems to be there. The universe has this weird type of pressure which comes from the properties of nothing, basically, in the modern quantum theory, that gives you an effective pressure because you can't exactly identify where a particle is. This uncertainty gives you an effective pressure, and that is our conjecture about the cause of the acceleration of the universe. Okay, so this turns out to be a headache for the cosmologists today. Let me first tell you how they made this breakthrough in going beyond the early data that just showed expansion. They studied the brightest objects in the universe, exploding stars, supernovae, which are thought to be essentially perfect bombs, certain types of them. And so if you can measure them nearby, you can calibrate, you can use them as your yardstick, basically. And then when you look far away, you find in this distant galaxy that here is such a supernova. You can't resolve it like this. This is a nearby one in our Milky Way. This is far away. But it's got the same intrinsic brightness, therefore you can infer its distance. And you find, because you can also measure the distance of the galaxy from its redshift, that this simply is faint. It's too faint. Therefore, the galaxy must be further away than you think it is. Therefore, the universe is accelerating. So this is the modern way. Data inaccessible in the 1920s. Actually, it took half a century to develop this sort of precision in getting data, and or more. And so there we have it. So this has led to what has been called the biggest problem in physics, let alone cosmology. So I want you to ignore the units on this picture, but there's a number there, which is the density of the universe that's required to give you this extra push. Okay, we call this the vacuum density, the interpreted as quantum effects that Lemaître actually conjectured had to be there. So that's what we measure. Now we can go back to our theories of the beginning of the universe, and we try to predict what they should be. And the best prediction is this. So all I want you to look at is the numbers. Forget the units. But you can see there are many, many factors of 10. There's about 120 factors of 10 difference between what we see and what we would have expected from our theory of our best theories of the beginning of the universe. So this is a big headache, and it's been called the greatest problem in physics. Okay, so, it's fair to say that we don't have a solution today to this problem. I mean, there are conjectures out there, but it's something that's challenging our latest studies of the universe, galaxy surveys, to try to find some clues as to what this this vacuum energy, this density of nothing, almost nothing, might be, which is causing this acceleration. Okay, I'm not going to tell you any more about the speculation behind this, but what I will tell you is one simple prediction of the acceleration of the universe. So here's a cartoon that tells you, shows you, there are actually billions of galaxies. It's how far out we can see with the very biggest telescopes, 15 billion light years. And then as the universe expands, you expect to see more and more galaxies, right? That would have been the old prediction before we discovered the acceleration. But because the universe expansion is accelerating, all these galaxies are moving out of our horizon. They're going faster and faster, okay? And in a certain amount of time, it's a bit sad, this is a prediction, it's a long time away, it's 140 billion years, the sun will have long died, but nevertheless, it's a prediction, we'll be the only galaxy left. Our Milky Way will be the only one that we can see. When we look with our telescope, we'll see nothing, no other galaxy. They'll all have gone, those billions of galaxies will have accelerated out of a field of view. So that is a fundamental prediction about if the universe keeps on accelerating. That's what we can expect. Of course, the acceleration might stop for unknown reasons, but this is our current best view of the very, very distant future. We really will be alone in the universe. Okay, so let's now turn back to the artists. So I want to now switch to dark matter. So dark matter, again, has... it's a fascinating subject. It's inspired our creative imaginations. I'll show you two visions of dark matter. This comes from sculptures, basically, by Cornelia Parker, a view of cold dark matter. And here's another one that is in a different type of universe, but equally, it's another view of what dark matter might be. Okay, so... how do we find matter that's dark, right? So the idea is the dark matter, it exerts gravity, right? Even though we can't see it, we have found that it's there. We've discovered its presence by its effect on the stars that we see. So stars, in this example, so they orbit around this galaxy, a sort of galaxy a bit like the Milky Way, okay? And if the galaxy is full of dark matter, this is going to have some effect on the stellar speeds. And you can say, well, maybe it's due to very faint stars or whatever that we just can't quite see. But then we've looked very hard for these faint stars, and if you can eliminate that option, then it must be something truly dark that's doing this. So it's a little bit like, eliminating all the possible explanations and coming to perhaps circumstantial evidence that something must be happening. Okay, so the person who pioneered this way ahead of his time, this was in 1933, is Fritz Zwicky, who lived mostly in California, originally a Swiss astronomer, and he talked about dark matter. His native language was German, so das dunkle Materia. And his idea was that let's study a cluster of galaxies, hundreds of galaxies. The most famous one was the Coma cluster at that time, actually thousands of galaxies. And he, again, thanks to the redshift with telescopes, was able, with his colleagues, to measure the speeds at which these galaxies were moving. Now, mostly they were just buzzing around inside this giant cloud, the cluster of galaxies. And so you had their random motions. Of course, the whole thing was moving away with the expanding universe. It was the random motions that intrigued him. And he realized that these galaxies should just be flying apart. It was just like a beehive or something. They should be dispersing. The cluster shouldn't be there unless it was full of dark matter. And he figured out how much there had to be, and in 1933, and he said that there must be 400 times more dark matter than light matter if the typical light matter is like a star, like the sun or something. So that was his number. And so the amazing thing is this rather crude inference from the data in 1933 has lasted, 90 years or thereabouts, and it's currently as good a value as we have, but we do have greatly improved observations. Okay, before I show you those about clusters, let's now first think about the Milky Way and galaxies like our galaxies. So that one of our nearest neighbors, the nearest galaxy like us to us, is the Andromeda galaxy. You can just see it as a fuzzy patch in the sky with a naked eye on a very dark side, constellation of Perseus. And you can measure the speed of the stars, and they mostly are rotating and going around in a disk. And so here you have the central part of the galaxy where all the stars are, and you measure the speeds of these stars, and as you go out, there are still some stars out here all the way out. And then even when you run out of stars, there are gas clouds, and you can measure those gas clouds, and they're with no stars at all. And you notice their speeds, basically, these yellow dots indicate the speeds just stay the same. So if all the mass was where the light's concentrated, the speeds have to go down because gravity is getting weaker as you go further out. But it's not, okay? So something strange is happening. So again, this is what you expect, this is what you see. And there was a huge discrepancy. And these two astronomers, Vera Rubin, who measured this in the optical from Matt Wilson, and Morton Roberts, who used radio techniques to look at the gas clouds, but concluded that there had to be a lot of dark matter, at least 10 times as much dark matter as you maybe 100 times as much as you see in the stars. Okay, so the next step then, we fast forward. That was in the 1950s. Let's fast forward half a century to recent studies, and finally we can now directly image the dark matter by using Einstein's idea that light paths are curved, space is curved by the effects of gravity. So light does no longer travels in straight lines because of the effect of a mass. And if there's more mass than you can see, then the light will curve even more in its path, and so you can infer what's going on. So here we have the concept, okay? So here's a galaxy full of stars and lots of dark matter maybe, and the light from a distant galaxy behind this one, way behind this one, will be going in this direction, but its direction gets curved, okay, and comes to our telescope. And so what you can then imagine you will see, this image will then, because if you try to rotate this, in and out of the screen, you'll see a circle, right? You'll see a circle of light. That'll be the lensed image of a distant galaxy. And the broader that circle, the stronger the light's curving, the more dark matter there must be. So that's the idea. And amazingly, this is what you see. Okay, with modern techniques, you take beautiful images with the Hubble Space Telescope, for example, and I'm showing you the best example. It's been called the golden lens, but others are, because if you're not quite aligned, you don't see quite the same symmetry as this. But anyway, you see this incredible, one distant galaxy way behind this one, its light is being turned into this. And the only understanding of this is that this galaxy must have a lot of dark matter, much as the amount that we deduced from studying the Andromeda galaxy, or our own Milky Way, from the motions of the stars. So all that hangs together. And so this is one galaxy. This is perhaps, tens of thousands of light years across, 30,000 light years. But if we now move on to Zwicky and his cluster of galaxies, we see exactly the same thing. For now, over 1 million light years, we're studying an entire cluster. So each one of these is like this galaxy. And we're looking at a way distant galaxy behind it. And again, its light is being turned into this beautiful arcs. And it's not quite regular because, there are other things that get in the way. You're not quite in the central line of sight. But anyway, we're mapping out the dark matter by studying the distortions of the background galaxies. We actually produce maps of dark matter. And the conclusion is that the dark matter is everywhere. Okay, so there it is, much more than in the stars. Let's ask another question. So I like this question because this is an example I'm going to show you where the power of computers has made a huge difference in astronomy. So naively, you say the galaxy is full of dark matter. We call this a halo of dark matter. So here's this is Andromeda actually. I've stuck in the middle, and there's some big giant shell of dark matter around it. But in fact, that's not the case. So when you do computer simulations of dark matter, you find that the dark matter clumps. It forms many, many clumps. I mean, it's the same amount of dark matter spread over all, but it's now in many, many clumps. And this is the galaxy, which you see in the stars. Of course, it looks nothing like the dark matter. The beautiful spiral arms. Each of these are thousands of bright stars, okay? The center of the galaxy, the central region with many, many stars in. But when you look in the dark matter, all this complexity of the stars isn't there. You're just seeing the underlying dark stuff within which the stars condensed from clouds or whatever. But that dark stuff is simply not a big uniform sphere. It's broken up into many, many clumps. And that's very important because it's breaking up into clumps is the whole way that, the gas forms in clumps, those clumps and the gas then make the stars, and it's the way structure evolves. So with one big uniform sphere, you probably would have had a very hard time making a galaxy, but because we say that the dark matter is in some sense unstable to making these clumps, that helps a lot to generate the universe we see. Okay, so the fact that the dark matter can form these clumps on small ones, big ones, this is a property that we can think in terms of temperature. That just means the random motions of particles for the dark matter, which probably consists of some sort of particle that we haven't discovered yet. And we say that it's cold, okay? Okay, so if it were hot or warm, it just wouldn't clump up because the random motions would stop it. But if it's cold enough, it would clump. And that, we think, is how galaxies are formed. So how do we test this? Well, here's a beautiful way this has been tested in simulations, again, but now not of one galaxy, but of a vast chunk of the universe. And so here you appeal to the power of statistics. You do a survey of 1 million galaxies. You measure their redshifts, and you look at their distribution in space. And if the dark matter is cold, you should have lots of clustering, clumpiness of these galaxies on the larger scales. It's hard to see the small ones, but the bigger ones you can trace out by studying where the galaxies are. And so in the blue, you see data. I won't even explain where this comes from, but these are 1 million galaxy surveys by astronomers. Okay, and basically they're looking further away into the universe using redshift to fill out this big cone of structure in the universe, which is projected in this plane. But in the red, you see from the computer, the simulations with the single assumption that the dark matter is able to clump, that it's cold, and that it doesn't interact with the ordinary matter. And then you say, well, wherever a clump of dark matter, I call that a galaxy, I assign it a certain amount of light, and lo and behold, I make a picture. And so you've demonstrated that this hypothesis is a beautiful explanation of structure, and now we're going out to basically 100 million, several hundred million light years. So the dark matter is not just in our Milky Way. It's not just in clusters of galaxies, millions of light years across. It's spread throughout the universe over hundreds of millions of light years. So just to give you some example, we've advanced a lot in computing power. So when these maps were first made, we could compute 100 million particles in the computer as points and let them cluster and see what happens. Nowadays, the biggest computers can do 1 trillion particles. It's an amazing increase in complexity one can do, but the results are the same. And so, but we can start to look for tiny deviations, which you haven't found yet. Okay, so let me try to summarize. The dark matter consists of something very weakly interacting because it's way out from where the stars are. It's not making any light. Therefore, we say it's made of some weakly interacting particles. Unlike the particles that make us or make stars, they do lead to nuclear reactions, they lead to light, they lead to chemical bonds or chemistry, all this stuff. The dark matter is invisible that way, therefore it must be weakly interacting. And we think it's probably a fundamental particle. That's the simplest hypothesis from the very early universe, but we haven't found it yet. Okay, so many attempts are being made now to look for this. And it's interesting that there are many, many hypotheses out there as to what these particles might be. And I would say a guiding line in theoretical physics is something like this, that everything that's not forbidden by the laws of physics is compulsory. It should exist somewhere, okay? And although most of this may have decayed, may have vanished a long time ago at the beginning of the universe, some relic of that could be the dark matter. So theorists who specify what the experimentalists might want to look for are full of ideas. Some seem far-fetched, others less so. But it's all relative, and it's all based on the premise that there must be dark matter. We haven't found it yet. What could it be? Okay, so here is one direction this reasoning takes us in. So, we can make new particles at extreme energies. We do that when we smash them together in big particle colliders. The early universe was our ideal particle collider. The energies achievable naturally at the beginning of time were incredibly high. So all particles that could have existed would have existed at the beginning of the universe. Fortunately, most of them decay in an instant and are no longer here. But if there's one survivor from that bizarre time of extreme energy, that could be our best candidate for the dark matter. Even though we don't make them now in stars, etc., it's a leftover relic from the beginning of the universe. So that's one of the major ideas behind the search for dark matter. It's a relic from the beginning. But unfortunately, there are many possibilities that this relic could be. It could be a heavy particle, it could be a lighter particle, and we try to think of ways that may guide our experimental colleagues to look for these things. Okay, and as the universe cooled down, these particles, which would have been there eventually, as the heat died away, they could be the dark matter if they're stable. We have to assume they're stable. Okay. So the first way we try to test this hypothesis is to go to the particle colliders and try to recreate the Big Bang, right? To smash particles together at such high energy that you can reproduce these initial conditions or something like it and try to make particles which might be long-lived enough to be candidates for the dark matter particle. And so this, in principle, is something you can do at this place. This is the Large Hadron Collider, currently our largest particle smashing machine. This is 27 kilometers across, and there's a tunnel underneath here in which you send particles in two different directions. They collide into each other at very high energy. You look for events when they collide together that carry, you see energy being, energetic things coming out, but we know energy is conserved, right? Fundamental. Momentum is conserved. But if you see events with missing energy, then that missing stuff could be a dark matter particle being produced. That's the idea. And so we've built, my colleagues have built these incredible machines to look for the results of these collisions, to detect tiny flashes of light that could have some missing component that would then lead you in the direction of dark matter. And the sad thing is they've found, so far, no evidence for dark matter. Okay, so far that doesn't mean to say that it's not there. That doesn't mean to say that we should stop looking. In fact, there are serious attempts now to build accelerators, particle colliders, that are 10 times the energy of the one I showed you in CERN, which means that costs something like, I think, 8 billion euros. And if you want something 10 times bigger, you have at least 10 times the cost, many more magnets, modern technology. It's something that would take you many years to build, but these schemes are on the drawing board to expand our search for dark matter, just because we may not have quite got close enough to the early universe conditions we need to make it. So here's another approach to dark matter. So we know how much dark matter there is, we measure it, therefore we know how many particles there are out there that might be this dark matter. And so these particles, they interact with us, they pass through us. And it's a little bit like Goldilocks, actually. If they interact too strongly with each other, then there are none left today, or very few left. If they interact too weakly with each other, there are too many left. So they've got to be just right, okay, in their interaction strength. So first, we know how many there are. And secondly, we can infer, if they're the dark matter, their strength. And we have a wonderful name for them. We call them WIMPs, for weakly interacting massive particles. Okay? It's always great to have a name for something. So we're searching for WIMPs out there, and we're searching now for the ones that are passing through us, okay? So forget the accelerators, let's put that aside, it's another experiment. But now the ones that are bombarding us, and there are many, okay? Every second going through you, okay? Through us, if we're right, that these are fundamental particles. The trouble is they interact so weakly, okay? You need a huge detector mass. It's no good having a human being. Our mass is far too little, and besides which, the only thing they might occasionally do is give you a random mutation or something, and that won't do you any good either. But what you want to do is go deep underground, have a huge mass of material, and look for tiny light flashes from these interactions. Okay, and we can predict roughly how many there should be. Okay, so it's an industry. It's going on all over the globe. There are many experiments. They have to go deep underground, deep under kilometer equivalents of rock, because the cosmic rays, the natural energetic particles that bombard the Earth's atmosphere, will also give you light flashes in these detectors, and you want to avoid them. But you want to have a huge rock mass to protect you. Okay, so here you can see that the experiments are spread around. We have our own one in the UK, in the Bolby mine, and there are several in the US. Mostly these are mines, or in some cases where you have mountains, you have tunnels, freeway tunnels that go underneath. You can then cave out experimental labs deep under the mountain. Okay, and the current record holder is the one in China at Yangyang, which is some 2.5 kilometers below the surface. Okay, Bolby is about 1 kilometer deep in the north of England. So here is the current state of the art. Gran Sasso in the Apennine Mountains in northern Italy. There's a highway that goes through the base of that, and they've carved out an experimental lab. Elena Avrili is the principal investigator of the experiment, and and her colleagues have constructed a tank with 1 ton of liquid xenon. Okay, so why on earth would you go for liquid xenon? Well, noble gases, noble elements are very clean. All the other things that you might think of for looking for these tiny directions probably have some natural radioactivity. They're impure for whatever reason. But if you deal with a noble gas, that's probably your best bet. And meanwhile, in China, and perhaps twice as much rock, also similar experiments are being done. I think they're currently up to about 0.5 ton of liquid xenon, but they're rapidly improving. And again, freeway tunnel through the mountain, underground lab that does that. Okay, so it turns out that they've found nothing so far. A ton is not good enough. Okay, so what do you do? Well, it's simple. You go to 100 tons, right? The bigger the better, because the more material you have, the greater your chances are of seeing this very, very rare event. Although there are lots of these particles passing through you, only very seldom does one give you this flash of light you want. Okay, so the more detector mass, the better. Okay, and as I said, you do it because the noble gases are very clean. So we can go to 100 tons of liquid xenon, massive detector, okay, and deep in a mine, okay. Costs a lot, but these are being planned now, okay. The trouble is there's no guarantee we're going to find anything. It's a bit worrying, and you may ask why stop at 100 tons? Well, it turns out that there is a natural wall you come to because there are tiny particles called neutrinos that come from the sun and from the atmosphere of the Earth that will pass through anything, and these will get into your detector, and these will give you reactions that you can't possibly avoid, and give you a background of light that will confuse any signal if you look too sensitively. So there's a natural limit to how faint you can go. So we're not there yet. It's another 10 years to get to our 100-ton goal, but that search is another very active thing that's going on. Okay. So there's another approach, which is equally exciting, but it's totally different. This is looking for another indication of these dark matter particles. So imagine our Milky Way or any galaxy full of dark matter, where the dark particles occasionally interact with each other. They collide off each other. And the theory that says they were made in the very early universe also says that they should and destroy themselves, because most of them have long gone. That is, they're created by extreme heat and they annihilate when they hit each other. Now, this happened frequently a long time ago when conditions were very hot, okay, But today, it still must happen with some probability. So it's a very rare event, but if you take a big enough cloud of dark matter, then every now and then, two particles will self-interact and produce, because they're massive, a flash of gamma rays. So we think that gamma rays are a great way to look in a dark place in the universe for a glow from dark matter. So what are the natural targets? Well, we go to the darkest galaxies we know about. So the Milky Way is, the center of it is full of dark matter, but there's lots of stars there, so it may not be the ideal place. But here are the darkest galaxies we know about, and you can see this is one that's pretty dark, just a pile of stars. And here you can barely see the stars. This one is the faintest one known. So this is an example of an ultra-faint galaxy. And remember, I said there are a few hundred times more dark matter than stars in the Milky Way, or whatever, in terms of the mass equivalence. Here it's thousands of times more dark matter than the equivalent mass in the light from sun-like stars, okay? And when you count the stars in these times, there are just a few hundred stars, right? So it's almost all dark matter. So it's the ideal place to look for dark matter. Okay, so we have the Fermi telescope, gamma ray telescope. It's been up there for a decade now, and it's monitoring for gamma rays in space. What does it find? Well, nothing so far. That's the bottom line. It's looked in the most promising places, and there are hints, but again, the argument is fine. We haven't seen it with Fermi. Let's build a bigger and better telescope. So that's okay. So here's another place that we look at, which is the center of the Milky Way, because in the center of the Milky Way, we're pretty sure from the theory, from the simulations, the dark matter has collected there. It's a big cloud of dark matter in the center, so that might be a good place to look. And there's a recent satellite called Gaia, which produced this amazing picture of the Milky Way. And there are 1.5 billion stars in this picture. So that's a significant fraction of the Milky Way galaxy. And this is the center. You see lots of dust clouds and things. But in this central region, we believe the dark matter is accumulated there, and maybe its effects will, we would hope, perturb the stars slightly. That we haven't seen yet, and that may come. But we can look there for the gamma rays. We point the gamma ray telescope there. And so, indeed, when you point the gamma ray telescope there, this band is just a mask to guide your eye, where there's other extraneous stuff. But behind the mask, in the center of the galaxy, when you take out all known sources, there's a glow. There's an excess glow of gamma rays. So for a while, people got very excited by this. This is exactly what you might expect. The shape is more or less spherical, is about right. The strength of the gamma rays more or less fitted what people expected from this argument about they're interacting not too strongly, not too weakly, etc. So all looked good. And then more and more data came in, and then finally this gamma ray telescope decided that indeed there were a number of, maybe hundreds of very weak sources there. Right? Probably stars, star-like sources, but gamma ray stars. We think they might be something like pulsars or X-ray binaries or some sort of slightly weird star, but in any case, it doesn't look like dark matter, which should be more diffuse. So the jury is sort of out. I mean, maybe the dark matter, some of it could masquerade as more point-like clumps, we don't know, but anyway, it's sort of negative. Okay, so let me take you now to the most exotic place for an experiment. So we've talked about deep underground in space. I now want to take you deep under the South Pole. Okay, why in the ice? Because the ice is incredibly transparent if you go deep enough, and that's another good place to look for flashes of light from dark matter particles that might do something. Here the story is a bit more complicated because the idea is, it's more convoluted, you might say. The idea is our sun is a collector. It's a giant collector of dark matter, right? The dark matter particles do enter the sun, and some will collect in the middle. And in the middle, some of them will again collide with each other, and they will produce neutrinos, these very penetrating particles, essentially pure energy and little else, little mass, but can penetrate more or less anything. But some of those neutrinos will then hit the Earth, and in the Earth, in the Antarctic ice, they will make particles called muons, which can give you flashes of light, okay, so elementary particles. by their interactions, because there's so much mass in the Earth for them to interact with. So it's a weird experiment, but here we are. You have to now drill kilometers deep in the ice, which is not easy. So you use steam. These are steam-powered drills, okay? And so they drill deep in the ice, and they lower strings of phototubes detectors. And just to give you some feeling for the scale, this is the surface at the South Pole, and this is the scale of the Eiffel Tower, okay? So it's an amazing experiment, and they have now hundreds of these strings of phototubes looking for light flashes coming from the direction of the sun, basically, because that's where these events come from before they hit the ice. And then, so you wait for when the sun is below the Earth, and then that's your best chance of looking for these signals. And this is the guy who leads that experiment, Francis Helton. And again, it's all very exciting, but so far they've found nothing. So my last example of a similar approach is, this is in Japan. Okay, so again in a deep mine where they're going to use a vast amount of purified water as your target, again for neutrinos from the sun. Okay, it's produced by dark matter. And so they're on the way to filling up this deserted mine with highly ultra-purified water, and many thousands of phototubes looking for these, and turn the lights off, and then you look for these rare flashes. So far they're up to about, I think it's 50,000 tons or so, but they're scaling this up, and so in less than 8 years, they will have 1 billion liters of ultra-purified water, and here are the engineers checking the phototubes and doing this experiment. Again, that's for the future. It's just to give you some feeling for where we're going in this field. Okay, so let me try to put things together to summarize for you. So we haven't found the dark matter yet, okay? But we're convinced it's there. So it's clear that we're running to the limits of what we can do with our current hypotheses. We're reaching this barrier where you can just build things so big, and then you run into either some natural barrier, or maybe you run out of money. I mean, no one is going to fund more than, say, the cost of one nuclear submarine for the cost of one science experiment, or some equivalent like that. There's some natural number that you can never get beyond. And I should say we're almost at that point in comparing costs, by the way. So the dark matter is everywhere, and it's true for the dark energy as well. For the dark matter, we would like to ideally have new ideas. Maybe our lack of success is because we're just looking in the wrong place. There's this famous, it's a little bit like, you go for a walk at night, you lose your car keys, and you go back to look for them, and you look under the lamppost, right? It's the only place you can see, right? But they could be anywhere. And so the same philosophy, it's a bit disconcerting. It's true for dark matter. We've only been looking so far in a small part of the possible space where the dark matter could be hidden. So we need to expand our ideas, expand our experiments. So this is one very important step for the future. And of course, there's a certain element of luck involved as well. But if you cover enough of your space of possibilities, then there's a good chance that will aid you in finding something. And as for dark energy, it's not quite the same thing. We do infer directly the acceleration of the universe. We interpret that as being dark energy. But ideally, we'd like to understand better, much better, where it came from to get over this terrible problem we have in the fact that it's so incredibly weak. It's this weakest force compared to this incredibly strong thing that's predicted by a simple theory at the beginning of the universe. What on earth is going on? Well, it could be, if it once was strong and now is weak, it's gradually decayed with time, right? And if that were true, then when you build your big telescope and do your next deepest survey, you should see a little more dark energy back in the past. You should see some evidence that it indeed is decaying. So this acceleration should not be quite as simple as we're finding now. It should be speeding up a little more, and maybe maybe changing basically from just a constant acceleration. And that would be telling us that perhaps in the past this dark energy was stronger, right? That would be the idea, to see acceleration further back than we can at the moment. If that were true, that would lend credence to the idea that it once was very big and it's just decayed away to being very small now. That would be an immense discovery if we found that, and we're looking very hard and we're building bigger and bigger surveys and new telescopes to test the idea of dark energy as you look deeper and deeper into the universe. So far, we've just gone basically back to halfway back to the Big Bang, which just means a few billion light years. But in principle, you can look much, much deeper with bigger and better telescopes. So that's the future for dark energy. So at the end of the day, we need bigger machines on the ground, under the ground, in space, to study the dark side of the universe. So it's a great problem for the future. So thank you.